do an example of dimensional analysis. So the task we've been set is to find the dimensions of this quantity, 1 over the square root of g rho. Rho is mass density, and capital G is Newton's constant of universal gravitation. And dimensions here means what do we measure this in? G is going to be a value with some units that go along with it. Rho is going to be a value with some units that go along with that. When we express those in terms of their base units of meters, kilograms, and seconds in our MKS system, what are the units of measure of this particular quantity? So to go about that, it's going to be a little algebra exercise, and we need to know what the units are for both rho and g. So rho is a mass density. We measure that in the units of mass per unit volume. So it's going to be kilograms per cubic meter. And I'm putting units in square brackets. So if we see in an equation an m, if it's in square brackets, that means it's going to be a meter. If it's outside of square brackets, that might be a variable that means, for example, mass. So try to use the square brackets to reduce confusion, if possible. And G, capital G, Newton's constant of universal gravitation, is, as the name implies, as far as we can tell, a constant everywhere and for all times. Its value is approximately 6.67 times 10 to the minus 11 in our MKS system, and we measure that. It is newtons times meters squared over kilograms squared. So those are the units for those two quantities. And for this particular problem, we don't actually need to know this value because we're just asked basically what are the units of this. All right, so let me set up an algebraic expression that just has the units in it. So from big G, that's going to give me a Newton times a meter squared over a kilogram squared. And from rho, that's going to give me a kilogram per cubic meter. And that is all under a square root. And that is all in the denominator. Now, everything is in terms of base units except for newtons. So I need an additional piece of information. I need to know that 1 newton, which is our unit for measuring force, that's actually a composite unit in base units. 1 newton is 1 kilogram meter per second squared. So I'm just going to substitute that in. 1 newton is 1 kilogram meter per second squared. So I'll do that. I have a kilogram times a meter over a second squared. I still have a meter squared over a kilogram squared. And then from the units of density, I will have a kilogram per cubic meter. It's still all under the radical and all in the denominator. All right, so looking at that, a lot of things are going to cancel out here. I've got a kilogram times a kilogram over kilogram squared. So that all goes away. I have a meter times meter squared over meters cubed, and that's all going to go away. So what we have for this is 1 over second squared square root, and in the denominator, which that's just a really weird way of writing seconds. So 1 over square root of g rho is a time. You put in values in MKS, and it will come out to be a number of seconds. In fact, this quantity 1 over g rho comes up quite a bit in astronomy. It's how long it takes something like a cloud of uniform density gas to collapse under its own gravity. It's called the free fall time. And its actual value, if you want an equation for it, is as follows. And this points out one of the limitations of dimensional analysis. Dimensional analysis is not going to be able to tell us that there's a factor of 3 pi over 32 in the equation, because 3 pi over 32 is a pure number. It doesn't have any dimensions. So dimensional analysis is really useful for helping find mistakes. If you have some dimensions on the left-hand side, some other set of dimensions on the right-hand side, and they're different, you can't reduce them to be the same, then you have to have a mistake. But just because the dimensions agree doesn't mean you're necessarily right, because there could be factors that don't have a dimension because they're pure numbers that are there as well. So you'd actually have to dig into the underlying equations for where this free fall time actually comes from to discover that.